In this video, I want to show you how to train a convolutional ResNet to become an autoregressive emulator for the Kuramoto-Sivashinsky equation, a fourth-order PDE that exhibits spatio-temporal chaos. We will do all that in JAX with a couple of libraries on top. For this, we will first define a reference solver by an pseudospectral scheme, which we're then going to use to create reference trajectories. So this is an example of how a spatio-temporal plot of the KS equation looks like. This will then be sliced into windows, which we're going to explore and use to frame the learning problem. After the definition of a data loader, we will implement the architecture using Equinox. Then we're going to train this architecture in a very simple supervised training loop running for about 4 to 5 minutes on my laptop here. Then we're going to assess the training, first in terms of the training loss, and afterwards we will make some test predictions and investigate how the error develops over time and how fast we decorrelate from the reference solution. And finally, we will also assess how the solution manifold produced by the emulator compares to the solution manifold produced by the reference simulator by comparing their spectra. And we will see that even beyond the time of decorrelation, those two match quite well in the low wave numbers. Let's get started. The channel sponsor Pasteur Labs is currently hiring SciML and software engineering positions. Check out pasteurlabs.ai/careers for more details. Hi and welcome to this new video. I'm very excited to extend this series where so far we've mostly looked into steady state predictions into something which is now temporal and uses an autoregressive paradigm, meaning that the output of the emulator or operator we're going to train is going to be fed back into its input and then it's iteratively applied to produce a trajectory. And for this we chose an interesting non-trivial 1D problem on the Kuramoto-Sivashinsky equation, which is a fourth order PDE consisting of a very familiar convection term. So this term you might have seen in a Burgers equation or in the Navier-Stokes equation. Then it has a second order term, which is typically associated with diffusion. However, it is on the right side of the equation and it has a negative sign, meaning that it is negative diffusion. So whereas diffusion would decay your solution, negative diffusion in the opposite produces new energy. And then we also have a fourth order term, which is a hyperdiffusion, but by its negative sign it acts dissipating. So in essence, the KS equation under a specific configuration exhibits spatiotemporal chaos, and this is an equilibrium of all these three components, so that we have the diffusion term producing new energy precisely in the lower modes, the nonlinear convection term moves energy between the modes, and then the highest term dissipates that. And this will run indefinitely and produces some very interesting spatiotemporal patterns. The KS equation is quite hard to solve because of the fourth order term. We will be using a reference simulator by a Fourier pseudospectral method. I also made a video about that, so we will not spend too much time on the reference simulator and we'll just use it as the data generator here. And our data trajectories on which we will train the convolutional ResNet are going to be warmed up that they are already within the so-called chaotic attractor, which is this pattern running indefinitely. Let's get started with the coding. So I already have here all the imports. So obviously we will need JAX. We will also need its NumPy and treeutils extensions. Then we will need matplotlib. We have Equinox. So Equinox is a deep learning framework in JAX. Then we will also be using Optex, which is for gradient processing and provides us with the Adam optimizer. And then we have a simple progress meter via TQDM. So then let's start by first defining some constants. And the first one I want to set is the domain size. And this one I will be setting to 100. This is very important. So this is essentially the physical domain size on which the equation is solved. So you can think of 100 space units if you want to introduce a unit system. That could also be meters. And it's very important that this is a high value because the KS equation does not, or in 1D at least, does not become chaotic below a certain limit. So typically this is around 50 to 60. So with 100 we are on the safe side in quotation mark that we have a chaotic trajectory. Then let's set the number of degrees of freedom. So this is what we will be using to discretize this domain, and we will set this to 256. And then we will also choose a time step size of 0.2. Next up, we have to define some constants with regard to creating the training data set. For this we will set the num samples for train, so how many initial conditions we want to use to create trajectories. In this one I want to set to 30. Then we also want to set the train temporal horizon. This essentially means we have, so let me finish that. So we have 30 initial conditions, and then we want to say how long of time we want to integrate them for and make this part of the training data set. And this one we will set to 100. Then we will set the number of warm-up steps. I already mentioned that in that we want to be within the chaotic attractor, and in the beginning we're not. So 500 is more than sufficient to make sure that we are within this chaotic attractor and not within the transient phase from the random initial condition to this chaotic regime. Let's shift enter that. Then let's also set some constants for testing. So let's say the number of samples for test will be 20, and the test temporal horizon will be 200. In the next cell, I want to copy the reference simulator. So I will just copy them in because I have a dedicated video on explaining how it works. I will have that linked up here. I just want to briefly go over that. So this is a class which is designed in a way to be an autoregressive simulator. So in that it has a constructor, but it also has a call signature, which basically takes a discretized state at the previous point in time and produces the discretized state at the next point in time, whereas the delta t is hard-coded. And it is a pseudo-spectral method, so meaning that we will see a couple of FFTs in here. As said, more details are in the video up here. One important difference is that in contrast to the video, I have changed the aliasing strategy a bit in that it is performed before evaluating the nonlinearity, but for the sake of our learning problem here, this is only a minor change. Okay, let's shift enter that, and then let's use it to instantiate the stepper. And since we're using pseudospectral ETDRK method, I also want to call it like this and say this is the KS ETDRK2 stepper. And for this, we will instantiate the class by saying KS ETDRK2 and then provide the domain size. We will provide the number of degrees of freedom and the hard-coded DT. Okay. Then we can use this class to produce our training trajectories. For this, we first need to set initial conditions. So let's do U0. And for this, I want to just use random initial conditions. That is because the initial condition for the KS equation does not matter. I mean, it still matters, but because it defines how the trajectory looks in very concrete details, but it does not affect that we ultimately end up on the chaotic attractor. And so we can just use some random start. So let's do jax.random.normal. So this will be pixel-wise normal distribution. So each degree of freedom will be chosen from a normal distribution. So we first need to provide a random key, jax.random.prng key, and then for simplicity let's set this to 0, and then we would say the shape of this initial condition shall be num samples train 1 num degrees of freedom. So what happened here? So we will create a tensor with 3 axes, and the first one will be the batch axis. Then we have a singleton axis with only 1 dimension, and then a number of degrees of freedom. And I chose this particular format to match later on that we will be using convolutional layer in our ResNet, which follows the pattern of batch, channel, spatial. So channel here means that how many physical variables are associated to each spatial degree of freedom. And here the KS equation, if we look at its definition again, we see it as a scalar equation. So this U only has a single channel or a single variable, you might say. That would, for instance, be different if we solved the Euler equations, which has in 1D 3 variables, or I think you get the pattern, or if we had the Navier-Stokes equation in 2D, we also had 2 channels for the 2 velocity components. So this is just one, and it will also be hard-coded. Then the number of degrees of freedom, I think this should also be clear. This is basically the spatial points within our domain extent that we want to have the domain discretized. And then the number of samples trained, this one we set to 30, so meaning we choose 30 initial conditions. And then importantly, we have to reduce the mean, so the initial condition is not allowed to have a mean for the KS equation, as this could lead to incorrect trajectories. So let's also leave the comment here and say KS requires zero mean initial conditions. And for this I will just use a quick hack, in that I say u0 equals jax.vmap on lambda u of u minus jnp.mean of u applied to u0. So what happened here, we defined a lambda function which is taking a state and subtracting its mean, which is valid for one initial condition. So you might say if we had an two-axis array with only the leading singleton channel axis and then the spatial discretization axis, and then we vmap that, which means that it transforms this function into something that operates on arrays with one additional leading batch axis. And this is essentially the case. So we will essentially remove the mean for all initial conditions separately, instead of removing the mean from the collection of initial conditions, which would obviously be wrong. So let's shift enter that. We can then use these initial conditions to produce our reference trajectories. And this is done by taking the stepper and applying it to u0, producing u1, then applying it to u1, producing u2, applying it to u2, producing u3, and so on and so forth. And for all the initial conditions in parallel, that we get our multiple training trajectories. And to simplify that process, I will copy in a function that I also discussed in another video. So this is a rollout transformation. It uses the scan function which is built within JAX, so which essentially does that job very efficiently for us. So calling a function on its output, and then stacking all the outputs together, so essentially stacking it into a trajectory. If you want more details, I have a video linked up here on this rollout transformation. So just for the syntax, so basically it takes a stepper function, so this is the etdrk stepper that we instantiated, and then requires how many steps it should roll them out for, and then returns a function which performs that rollout. This is to be in the spirit of JAX. So let's create a trajectory by saying rollout on the etdrk2 stepper, and then we need to define for how many steps we want to roll out. And so we will roll out for both the warm-up steps and the actual steps that we want, such that we can then discard the warm-up steps. So let's do drain temporal horizon plus number of warm-up steps. And then we will also use include init true to include the initial condition. So instead of returning a trajectory of, well, we set the train temporal horizon to 100 and 500 warm-up steps. So instead of returning a trajectory of 600 steps, it returns a trajectory with 601 entries, with the additional entry being the initial condition. But wait, so this is not it yet. So rollout would just transform the stepper as if being applied to one initial condition. But we had now 30 initial conditions. So now we will use another magic of JAX, and I think this can be a bit overwhelming right now, but I hope you can still stick with me here, and that we use jax.vmap on this rollout transformation. How and why does that work? So rollout does not produce the rollout. It rather returns a function that we could then query. So if we didn't do the vmap, we could then say apply this to u0. However, u0 does not have the pattern that we wanted to have. So it is not just a single state, it's multiple states at the same time. So the function produced by rollout will then be transformed again using vmap to now turn this into a function which takes a set of initial conditions, so this 3-axis tensor with the leading batch axis, and turns that into a 4-axis tensor with again a leading batch axis, but then a squeezed in axis which has the number of time steps. So let's apply this to u0, and then we can take a look at its shape and see it's 30, 601, 1, 2, 56. So this one should be clear. So now we have 601 entries, because this is the time axis, you might say. And then we have 30, which is the batch axis. Let's take a look at one of the trajectories. So of course we cannot plot all of them, that would be a bit overwhelming, but we can plot one of it. And let's use an imshow for that. So plt.imshow on trajectory being indexed at 0, 0. So why are we doing that? So we do a 0 here to index the 0th batch ID. Then we do a colon to index all the time snapshots. Then we do a 0 to index the channel dimension or to squeeze it out. And then a colon to do all the spatial points. And then typically I like to do a transpose here because otherwise the spatial temporal plot would be running from bottom upwards, and now it is going left to right. And then let's set the CMAP to RDBUR. I really like that. And set the Vmin to -2 and the Vmax to 2. Okay, here we go. Maybe let's also attach some labels to the axes. So plt.x label shall be time and plt.y label shall be space. And then essentially in the color, we see the corresponding value. Now I hope you see what I mean. So in the beginning, we have this kind of transient phase. So we start at a random initial condition that's barely visible. So it would be like pixel-wise noise. And then you see in the beginning, it's still a bit faded. And then it turns into these very beautiful spatial temporal chaotic patterns that the KS equation is known for. And it has reached that state, at least visually speaking, after 100 time steps. And we decided to do 500 time steps of warm-up, which should be more than sufficient. Of course, that could vary a bit between the trajectories. So for instance, if we change to another trajectory number, it looks a bit different. And here you see it reached its chaotic pattern, at least visually, a bit later. So with 500, we should be on the safe side. Okay, let's go back to the 0th initial condition. Then let's say we slice out the warm-up steps. And for this, I want to rename that. So let's call this one here, let's do a rename and say this is trajectory with warm-up. And then we can override that and say trajectory is just the trajectory with warm-up at all samples, so with a colon, and then from the number of warm-up steps, num warm-up steps upwards, so that we slice them out. And if we do that, we can take a look at its shape and see now it's 30, 100, and 1, 1, 256. We could also quickly make a plot of it and see trajectory without warm-ups. So just have that one here. And then we essentially see is if we took that part of the spatial temporal plot and just plotted it separately. So you see this very distinct feature, and it is again visible here. Okay, so this is for the training trajectories. So now we have 30 of these 2D slices, you might say. Let's also do the same for the testing. So let's say we also want different initial conditions for test. So U0 test is again JAX random dot normal. And now let's use a different pseudo-random number key. Let's say 1. And now we want to draw num samples test, 1 num decrease of freedom. And we will again use the same strategy to remove the mean by saying U0 test equals JAX.vmap on lambda u minus jnp.mean applied to u, and this applied to U0 test. So same as before. We can take a look at its shape again, just to be sure we did everything right. So it's 21, 256. Then let's also evolve them in time. And since we don't have to look at them into detail again, we will already slice away the warm-up steps. So let's call this TRG test. Sorry, TRG test is JAX.vmap applied to Rollout, applied to the KSETDRK stepper. And now the number of steps is the test temporal horizon plus the number of warm-up steps. We will again include the initial condition and then apply this to U0 test. And then afterwards, we will already slice with colon and then number of warm-up steps upwards. And then we can take a look at its shape. Oh, I see this, of course, should be trajectories test. And then I think, yeah, no, the shape matches that, it's 201. So now we have both the training trajectories and the test trajectories done. Later on, when we will then test our emulator, we will run it for as long as the test trajectories are. So we will autoregressively roll out for 201 steps. But this is not what we will be doing during training. So we could, but this is a very suboptimal way to do that with regards to the learning problem in the parameter space of the emulator. So rather, what we want to do is we want to further slice our trajectories. So here we have 100 or precisely 101 time steps across our 30 training trajectories. And then during training, I want to do a one-step supervised training, meaning that we will predict one step into the future only. We will not predict multiple steps into the future autoregressively, just one. And in order to do the learning problem, we will then use a stochastic mini-batching, which samples across time and across the different trajectories. So think of it, it's very hard to explain that with a 2D screen, but imagine we had our 30 initial conditions kind of like lined up, and you see kind of a cube structure, if you can follow my mouse cursor. And then we will sample windows of length 2 within this 3D tensor, you might say, and those will be part of one mini batch update. Precisely, we will then do around, I think my batch size I wanted to use was 20, so we will then randomly sample 20 out of these 3-axis tensor. And in order to pre-process that a little bit, I will already pre-slice the tensors. So I will try to slice the large tensor into something which has only windows of 2. Okay, bit more difficult to explain than to actually do. So let's define a function I want to call slice windows of 2, and this one should take one trajectory. So again, later on we will be using this JAX VMAP paradigm to make it operate on our batch of trajectories. So let's say it takes one trajectory, and this one trajectory now does not have this leading batch axis and only is this 3-axis array. Its leading axis is now the number of time steps that are in there, and for the train trajectories that was 101. So let's extract that and say number of time steps is one trajectory dot shape indexed at 0. So the length of the leading axis. And then essentially we will go over this time axis and slice out all possible windows of length 2. And if you have a trajectory with 101 time steps, there are 100 windows of length 2 in there. And those we want to get. So let's create a list, an empty list for now, and then make an iteration and say for I in range of num time steps -1, do the following: windows.append one trajectory sliced at I colon to I plus 2. Sorry, I plus 2. So we will use +2 here because the slicing or the ranges in Python are excluding the last element. So essentially, imagine for instance, I is 5. So we want to get the window of length 2 which starts at index 5. So this includes index 5 and index 6. And so what it does is takes the time axis and slices it at 5 to 7, and this gives us 5 and 6 essentially because 7 is not included, and then append this to the list of windows. And then later on we can stack these list of windows together into one array again. So we will say return jnp.stack on the windows. This operates on one trajectory. Let's again use the VMAP paradigm to make it operate on the entire training trajectories, and call this subtrj being jax.vmap on slice windows of 2 applied to trajectory being the training trajectories. Then let's take a look at its shape. And now we see, oh, it gets a bit more complicated. Now we have 5 axes. So we again have the leading axis being 30, because we have 30 different initial conditions corresponding to 30 different trajectories. And within these 30 trajectories, we have 100 sub-trajectories or windows of length 2. And each state within the window is a single channel together with 256 degrees of freedom. Let's give these axes some name because it can get confusing. So essentially what we now have is num samples train, which was 30, then num sub-trajectories. This is nothing we explicitly defined. This is something that kind of was implied, because if we have a 101 length trajectory and want to slice out windows of 2, then this essentially gives us 100 subtrajectories. If we sliced out windows of 3, it would have 99 subtrajectories, and so on and so forth. And then it's 2, 1, number of degrees of freedom, and this 2 is because we have windows of length 2. And we need windows of length 2 for one-step supervised learning, because we need an input and an output. Think of it like in supervised setting, this is the input feature and the other one is the output target. So let's rerun that to have that encoded as well. So next up, I want to merge these two batch axes, because this is what I meant earlier. Later on, when we do the mini batching, we will sample both out of the different trajectories and the different time. So we can merge these two together. So this is 30 and 100, but essentially these are two batch axes, because we batch both over the number of initial conditions and over time, because we already have the length of time we need. So we merge these two batch axes. So merge the two batch axes. And we will say this will give us the train data. And we can merge two leading axes by just using concatenate. It's a little bit of a hack here. So we will do subtrajectory and concatenate it. Then let's take a look at train data.shape. And now as said, this will be 3000, 2, 1, 256. So this is, well, let's already give him some name and say that this essentially is num samples train multiplied with num sub trajectories. And this will be, as said, 3000, 2, 1, and then the number of degrees of freedom. So what does it mean to have these subtrajectories? Let's plot one of these subtrajectories. And for this, I want to use a regular plot with an x-axis on the x and the y-axis being the corresponding value. Let's do plt.plot on train data. And then I want to slice out the 0th of these 3000 windows. Then I want to plot all the two states within the windows. So I use a colon here. I use 0 again to slice out the singleton channel axis. And then I use a colon again to plot all the number of degrees of freedom. However, if I did exactly that, then matplotlib would interpret it in that I want to plot 256 different curves with 2 entry, but rather I have 2 curves with 256 entries. So I do a .t here, and then if we shift enter that, we get the following image. So essentially here on X, this is essentially the index within space. So it's not space units, because space would run from 0 to 100. So here is 0 and there is 100, but rather it's from 0 to 256 indices. Let's add a label to just call this space here. It's very generic. But essentially what you see here in the blue curve, you see the input, and in the orange curve, you see the output. And now imagine it like this. You get 3000 of these pairs of blue to orange pairs, and your network, your convolutional network, has to learn the mapping from blue to orange. And you see here the difference is not that big. I mean, at some points it's noticeable, but other points they mostly match as well. And we could also maybe look at another of these pairs. So let's maybe take a look at the 100th pair, and here we see they are almost identical, the 400th pair, and so on and so forth. But essentially this is what constitutes our training data. Let's continue with implementing the architecture. So far we've prepared the training data. We have these windows of length 2. Now we need the emulator architecture. And I want to implement a ResNet. And a ResNet, it's a sequential architecture of blocks. It has a lifting into a hidden dimension, and then some processing blocks and the projection back into the dimension we want or the shape we want. So we will try to implement it in these two parts. So we will first have the implementation of our ResNet block and then the full ResNet. So let's start by implementing the res block. And I want to be very specific about the type of res block we will be using here. So let's call this the res block for residual block. And let's be more precise in that it is a post activation, because ResNets usually come in different flavors. This is the more legacy version of ResNets using post activation, and it has periodic boundaries and it works in 1D. So very long word. And it should subclass from Equinox module, because we will use Equinox as our deep learning framework. And then we need to define the attributes this res block has. And a ResNet block comes with two convolutions. So it has a convolution 1, which will be an equinox.neuralnetwork.conv1d. And then it has a second convolution, which will be equinox.neuralnetwork.conv1d as well. And then it also has an activation. And in order to type the activation, which is required for the attributes in this Equinox module, we need to import the callable typing. So from typing, import callable, and then we can say activation is a callable. And then before doing the constructor of that module, I want to do its call signature, so the forward pass, so def call, which requires us to get self and then provide x. So x in that sense is just the variable name of whatever comes into that block. More precisely would be if we call it u, because then it would also match what we have in the ETDR k-stepper for the chaos equation. But here I think it is more commonly agreed to call that x here. Okay, so what does the res block do? So first it saves its input x, or more precisely, what does the post-activation res block do? And it first saves its input x in temporary variable, and let's call this x skip. And then essentially it first performs an convolution and say x is self.conv1 applied to x. So we will just override x here as our temporary working variable. Then it applies the activation, so self.activation applied to x. Then it applies the second convolution, so x equals self.conv2 applied to x. And then it combines x with the skip connection, so it says x is x plus x skip, and then applies another activation. So x is self.activation of x, and then returns x. So essentially what we have here is we have a processing path for which the x goes through, and then there's a residual path or a skip connection. So we just take the input and push it past the actual convolutions and the first activation, and then we add it with whatever was processed and then perform the activation. Okay, cool. Let's also define the constructor for that class and say init. And this one takes self, and I want to have this very minimal, so this one just knows the number of hidden channels or whatever kind of number of channels it operates on, which will be an integer. And we need to provide the activation function, which was a callable. And then in the style of Equinox, we have as a keyword-based argument the key, which is the JAX pseudorandom number key. And this is required for reproducibility. And then essentially in the constructor, we have to do three things. We have to save the activation function as the attribute, and we have to instantiate two convolutional layers. So for this, we need to split our random key into two separate keys that are responsible for instantiating their corresponding convolutional layer. So let's say the C1 key and the C2 key for convolution 1 and 2 respectively are given by jax.random.split on the key. And then we can say self.conv1 equals equinox.neuralnetwork.conv1, and then this requires us to define the number of in channels. So the in channels is the hidden channels. The out channels is also the hidden channels. Then we need to define the kernel size. So I want to change to keyword-based arguments here. And this one I set to 3. Then we have to define the padding. So by default, the padding would be 0. But if we did a convolution with kernel size 3 without padding, this would essentially shrink our spatial resolution by 1 on both ends. So essentially, we set the padding to same such that we retain the spatial dimension. And then, importantly, we set the padding mode to circular. And circular essentially gives us periodic padding, which is in correspondence to the periodic boundary conditions that we also use in the Kuramoto-Sivashinsky solver. And that is very crucial here. And the key is going to be the C1 key. One important remark is that this option for padding mode requires a recent version of Equinox, so that's a very recent release that supports more than just constant padding, more than just zero padding. So I will just leave that as a remark here. So requires an up-to-date version of Equinox. The second convolution is instantiated similarly, so I will just copy paste that and say conv2 is essentially also convolution 1D instantiated, but using the second key. And then finally we can save the activation function by saying self.activation equals activation. So let's shift into that such that we have our ResNet block. Let's use this res block to build the full ResNet architecture. Let's create a class and call this the ResNet periodic 1D. It's again subclassing from Equinox module, and then it has three attributes. It has a lifting, so this is essentially the first processing layer that takes the input state and processes it such that it can then be used within the ResNet blocks. And this shall be an equinox.neural-network-conv1d. Then we have blocks, so this is essentially these sequential block structures are meant, and all of them are of this particular block type we just defined. So this is essentially a list of ResNet block post activation periodic 1D, and then ultimately we will have a projection which is equinox.neural-network.conv1d again. So again, let's first do the call signature. So def__call self and x. So this essentially, as mentioned, goes through the steps as following. So first it applies the lifting. So x is self.lifting applied to x. And then we iterate through the blocks. So for block in self.blocks, apply it on x. So x is block applied to x. And then ultimately we will have x is self.projection applied to x, and we can return x. Okay, let's do the constructor, which constructs all the three attributes. So let's do __ init with self. And then what do we need to provide? So we need to provide the number of hidden channels. Implicitly, we will assume that the state we are operating on is always only single channel. It's of course to make the interface a bit simple here. Then we need the number of blocks we want to set. We need to set the activation function, which is the callable. And then ultimately, again, we need a pseudo-random number key for reproducibility. Then first, let's split the key in as many keys as we need. So we need a new key for the lifting and the projection, and we need as many keys as we want to instantiate blocks. So let's call this the lifting key, the L key, then the block keys and the write key. And then I will place an asterisk in front of the block keys. And if I then say jax.random.split the key into number of blocks plus 2, it will split it into, let's say for instance, number of blocks is 5. It will split it into 7 keys, place 1 in the left key, place 1 in the right key, and place the remaining 5 into a list of block keys. Then we can instantiate the lifting. So self.lifting is equinox.neural-network.conv1d. And for the lifting, I want to use a 1x1 convolution. You could also say a pointwise convolution, which just adjusts the channel dimension. So it goes from 1 to hidden channels. And it does so by using a kernel size of 1 without padding, because with kernel size 1, no padding is needed, and uses the L key for that. So key is L key. And as you see down here, later on in the call signature, we do never use the activation. So the activation is within the blocks, meaning that the lifting and the projection are non-activated layers. They are 1x1 pointwise linear convolution, no activation. Then we can instantiate the blocks. So self.blocks is a list, and I want to use a list comprehension here, and that we say resBlock post activation instantiated at the hidden channels with the respective activation function and the key being k, and we iterate over the block keys with saying for k in block keys. So this essentially, when we have 5 block keys, we'll instantiate 5 different blocks and append them together in this list. And this list will then be later on used in the call signature to actually execute the blocks. Then let's do self.projection, which is equinox.neuralnetwork.conf1d again. And now this operates opposingly, in that it goes from hidden channels to 1, because after the processing is done with the ResNet blocks, we want to match down back to single channel, because we want to have the ResNet as being a state-to-state mapping, in that the input state, the X here, has the same shape as how it is returned. So this one will be hidden channels 1 with a kernel size of 1 and the key being the projection key. Sorry, I said R key, but I meant P key. Okay, so now this should work. So this is our ResNet in 1D. So let's start a training loop for this network. For that, I want to define some constants we will be using for training. So first, some architectural constants. So I want to set the hidden channels of our ResNet to 26. And I want to use 5 blocks. So number of blocks being 5. The activation, sorry, misspelled that, shall be the ReLU. So JAX.neuralnetwork.ReLU. Then the initialization seed for the network, I want to set to 42. I want to set the learning rate of our Adam optimizer to 3e-4. I want to set the shuffle seed. This is for the random mini batching to 99. And I want to train for 30 epochs. So first step within our training loop, I want to instantiate a new emulator, and let's call this the KS ResNet emulator. And for this we will instantiate our just so created ResNet with the number of hidden channels as given by the constants, the number of blocks as well, and the activation. And the key shall be jax.random.prng key on the initialization seed. Then let's instantiate an optimizer. So this is going to be a very classical Equinox JAX optex training loop. I will go over this a bit more quickly. If you want to have more details on that, I have a video linked up here on a very simple example. So let's do optimizer being optex.addon on the learning rate, and then we can start with defining an optimizer state being the optimizer.init on equinox.filter of the KS ResNet emulator with the filtering rule equinox.isArray. So now the opt state contains a representation of the trainable parameters and some additional values needed for the Adam optimizer. First, I want to define a loss function. So let's define the loss function, which is based on the model as well as a batch, and the batch shall be batch of data. So if we take a look again at the train data, which was up here, we saw it was 3000-256. We will now do a mini batching, which splits this 3000 into smaller batches, and this batch size, let's say for instance, will be 20. Then we have each batch being an 4-axis tensor with 20, 2, 1, and 256. So only a subset of all the batches. However, it will still be a 4-axis array. So we can kind of expect such a shape in the loss function. And as mentioned, with these windows of 2, we essentially have an input and an output that we want the model to learn. So let's call this also x and y. And we can extract that by saying batch indexed at all batches. So here, of course, this will, as said, will not be 3000, but rather be the batch size that we will choose later on. And then 0 for the first time frame or the first snapshot of the window. And then batch at colon and 1 for the frame thereafter, which will be the corresponding target. Then we can use the model to make a prediction. Let's call this y prediction. And for this, we will batchly execute the model on the input x. So we will say jax.vmap on model applied to x. And then we can simply compute a mean squared error, an MSE, by saying jnp.mean of jnp.square of y prediction minus y, and return this MSE. So given one batch of data, so a subset from this train data array, together with the current state of the model, which will end up to be this KS ResNet emulator, we can produce one loss estimate. Then we can use this loss function as part of an update function that updates the parameters, the weights and biases within the emulator. So let's call this the step function. And this step function takes the model, the state, as well as this batch. And now state will be the current optimizer state. And it first produces a loss together with a gradient estimate by applying the automatic differentiation engine on the loss function, but in its filtered version. So we will say equinox.filter value and grad applied to loss function, and then this applied to the model and the batch. The gradient can be plugged into the optimizer and the state to produce an update and a new state. So let's call this updates and new state by saying optimizer.update on gradient, state and model. And then we can use the updates to update the weights and biases within the model by the Equinox apply updates method and say new model is equinox.apply updates on model and updates. And then ultimately this function returns the new model together with the new state and the loss. And since each update step is the greatest computational effort in the training loop, we will JIT compile that, but we have to be careful that we use the filtered version in order to make that correctly work with the Equinox modules, and say add equinox.filter JIT on this step function. Then we can use this step function as part of our training loop. And this will be a nested loop. The outer loop will be over the number of epochs, and the inner loop will be over the mini batches. First, I want to instantiate a shuffle key, and the shuffle key will be jax.random.prng key on the shuffle seed. And then I will create an empty list to record the loss history. So train loss history shall be an empty list. Then we will iterate over all epochs. So for epoch in range of number of epochs. Here we have it. And then in each epoch, we will make mini batching. But so far we don't have a data loader yet. So I will just copy in a very simple JAX-based data loader. So let me go to one cell above. So essentially this data loader will be a generator. So it has this yield signature. So we can use it to create a for loop. And it needs us to provide the data. So in that sense, this will be the train data we prepared so far. It requires us to set the batch size as well as a key, because of course this mini batching is also a stochastic mini batching, so anything random in JAX needs to be reproducible, so it needs to be handed over a JAX pseudo-random number key. So let's shift into the data loader, and then I think I forgot to set the batch size actually. So let's add that. So batch size, and I want this to be 20. So in each update, we will have 20 of these windows of length. Now going back to our loop here. So we now have the outer loop over the epochs. And then in each epoch, we first need to split the shuffling key into a new key that will be used for the current epoch of mini batching. So we'll say shuffle key, and sub key is going to be jax.random.split on the shuffle key. And then we can iterate over all the mini batches by saying for batch, or you might also say mini batch in data loader applied to the train data on batch size being according to the batch size we just defined, and the key being the sub key. And then for each batch, I want to call the step function and override the current state of the ResNet emulator. So KS ResNet emulator, comma optimizer state, which will also be overwritten, comma loss, which is going to be produced, is the step function called on the KS ResNet emulator together with the current opt state and the batch of this current iteration. And then ultimately I want to append the loss to the training loss history. So train loss history training.append loss. This is our training loop, and in order to get some diagnostics on the run, I will just call a tqdm here and also wrap a tqdm around the inner loop. Then let's execute that. So we see an tqdm meter for the outer number of epochs loop is spawned. So we do 30 iterations. So we do 30 epochs. And then a second progress meter is spawned that is for the inner loop over the mini batches. And we see that for each epoch we do 150 mini batches. And that also makes sense with the batch size of 20. This corresponds to the 3,000 samples that we have, or total samples that we have available. I will spare you this training time and see you after the training has finished. Okay, we are back with the training. It took longer than in my preparation, and that was because once I stopped the recording for skipping to the finish of the training, I actually started the rendering process, and that of course affected the training performance. And I mean, I'm just using this poor laptop CPU here. Likely if you run that on your CPU, it will be way faster, let's say 4 to 5 minutes. Probably on a GPU, it will be even faster. I would guess it's around a minute on a GPU. Okay, nevertheless, now we finished. We did all the 30 epochs, and you see all of them were conducted here. Let's first inspect the training loss. So let's do plt.semilog_y to have plotting with a log axis on the y on the train loss history. And let's shift enter that. And here we go. So let's maybe attach some labels. So plt.x label, and x is going to be update step, and plt.y label is going to be train loss. So what do we see here? So first we start at a training loss that is around a little over 10 to the 0, let's say almost 2.0. And then we have an initial very fast transient phase where we decrease by 2 orders of magnitude, 2.5 orders of magnitude, and then there is some even more decrease all the way to 10 to the -3, and then we enter this very noisy regime, and probably we could have run our training even a little further, but I believe this should be a good state for now. Very important, here we see update step. So this is not epoch, this is not batch ID, but this is the update step across the epochs. So we see we have 30 epochs, and in each epoch we do 150 mini batches. That means in total we do 4,500 updates. And this is essentially also where our training loss curve ends, after 4,500 steps. Now we have our network trained. And this is the training loss. And if you recall, we trained the network of doing one-step prediction into the future across time, across trajectories. But since it is an autoregressive emulator, its task is not just to predict one step into the future, but to predict multiple and do it autoregressively. And this is what we will be testing it on. So for this, we need to make a test prediction. And this test prediction is now on a different data. So the data is still on the same chaotic attractor, but has different trajectories. So it's not seen during training. But I believe that even if you did the testing on the train data, you would see similar patterns, because the difficulty now is temporal generalization. It's not generalizing to different initial conditions. It's not generalizing to a different configuration of the KS equation. It's generalizing to doing more than just one step into the future, doing 100, doing 200 steps into the future. Okay, cool. Let's try that. And let's do a test prediction. And for this test prediction, we again use the pattern that we had before. We will use vmap transformation on the rollout transformation. So jax.vmap on rollout, but this time we will not roll out the reference stepper, but rather we will roll out the train network. So we will do ks ResNet emulator, and the number of steps we want to roll out is test temporal horizon, and we will also include the init with include init true. And then where do we start? So we start at the test trajectories initial conditions. So trg test, and then at :0. So if you recall, this is going to be the start of the warmed up trajectory, because if we go all the way back up where we prepared the data, we saw that for the trg test, we rolled it out for the test temporal horizon and the number of warm-up steps, and then cut away the number of warm-up steps. So essentially now it will not start at U0 test, which was this pixel-wise normal noise, but rather at a warmed up state. And we have 20 trajectories now. Okay, let's execute that. Go, should take a couple of seconds to produce that. Here we go. And now we have the test prediction. Let's also take a look at its shape. So it should now be of the same shape as the test trajectory. Let's confirm that and say test, or TRG test, sorry, dot shape. And now what are we interested in? We are interested in an error rollout. And that means we now have this kind of 1 to 56 axis. So this kind of represents one state. And then for each state, we have 20 samples across 201 time steps. And this dimension over the time is kind of this sequential dimension. And we want to see how does the error develop over time. Because right in the beginning at index 0, the error will be 0 because both trajectories start at the same initial conditions. But then they will start to deviate from one another. And we are interested in how strongly do they deviate from another. The first metric I want to look at here is the mean normalized root mean squared error. For this, I will again use this VMAP paradigm. So first let's define a function that performs the comparison of two states, so which assumes we are only giving it a 2-axis array with 2 states. Let's call this nRMSE with prediction and reference. And it produces first a difference norm by saying jnp.linalg.norm of prediction minus reference, and then it produces a reference norm with jnp.linalg.norm of the reference. And then it returns diff norm divided by reference norm. And the reason we chose a normalized error here is such that we kind of have this value range from 0 to 1. So 1 meaning that our difference norm is of the same magnitude as the reference norm, and it essentially means we have totally lost the reference solution, or we have totally done something different than the reference solution. So now how does that work? So this function operates on 2 states. And now we basically have 2 additional axes. So we have the batch axis and we have the time axis. Now we will use 2 nested VMAPs to apply that nRMSE function to the test prediction together with the test trajectory. So let's call this the test nRMSE trajectory set, which will be JAX.VMAP applied to JAX.VMAP on nRMSE, and then applied to test prediction together with test trajectory. Oh, sorry, I got that wrong again. So it's trajectory test. Let's take a look at its shape. So this set now has the following shape: 20 and 201. So because for each sample, it now has the nRMSE at each time level. And now we want to compute the mean of that, but not the mean over time, because we're interested in the temporal development. So we take the mean only over the batch axis. So let's call this the mean test nRMSE trajectory, because the names get a bit confusing here. And for this we will use jnp.mean of the set, and we will say axis 0 to only compute the mean over the 0th axis. And finally, we can then take a look at its shape and see it is 201. And this now allows us to nicely plot that and say plt.plot on mean test RMSE trajectory. Let's limit the y-axis to 0 and 1, activate the grid, and attach the x label of being time step and the y label of being mean nRMSE. And now we see the following. So right in the beginning at time step 0, as expected, we have 0 loss. And then over the time, we develop a crater loss. And that is also expected because the further we go in the time, the more likely we are to be away from the reference trajectory. Particularly, we will cross the threshold of 1.0 after, let's say, roughly 90 to 95 time steps. So this is kind of an expected error trajectory. Of course, there's a lot of improvement potential for the particular emulator, and I would encourage you to play around with the notebook. You can download it via the link in the video description. So the mean in RMSE is one metric to look at here. What is also very interesting would be to look at the correlation. So how long do we still correlate with the reference? So for this similar pattern, we will also use a function that computes a state-wise correlation. So let's call this the correlation, and this takes a prediction and the reference. And the correlation is computed very easily. So we will first normalize the prediction and the reference. So prediction normalized is prediction divided by jnp.linarc.norm on the prediction. And we will also normalize the reference. So reference normalized is reference divided by jnp.linarc.norm on the reference. And then essentially the correlation is given by the element-wise dot product. So we will do return jnp.dot. But since the prediction and the reference still have shape, so they have this channel axis, we will first flatten them into a vector to have the dot product operate correctly. So we will do prediction normalized dot flatten together with reference normalized dot flatten. So let's shift enter that. And then in a very similar pattern, we will nestedly vmap the correlation function to the test prediction and the test trajectory. So we will do test correlation trajectory set with jax.vmap on jax.vmap applied to the correlation, and then this applied to the test prediction together with the trajectories test. And then similar pattern, we will take the mean over the samples, because we now have multiple correlation trajectories, one for each particular sample. Maybe it would also be interesting to plot them together. Let's take a look at this. So let's do plt.plot on test correlation trajectory set.t. So essentially what we see here, or maybe let's add a semicolon and limit the y limits from 0 to 1, because 1 means that we are fully correlated and 0 means we fully lost correlation. So usually a value of 0.9 or 0.8 is chosen as a threshold of high correlation, meaning that when we are going below this threshold, we lost correlation with the reference. And now you kind of see that in color, we have this for all the different trajectories. But you would see that, well, approximately something that follows the mean would be the orange curve. Let's do that, and let's do the mean test correlation trajectory with jnp.mean of the test correlation trajectory set, and let's do this over axis 0. And now if we correspondingly plot the mean test trajectory correlation and limit the y limits to 0 and 1, we essentially get this. So this should be roughly the orange curve, I believe. Let's also add a crit here, and then add the x label being time step and the y label being mean correlation. We now see the following. So as said, if we choose a threshold of 0.8, then we are correlated, let's say, until 60, 65 steps-ish. Maybe let's make it round, let's say 60. So if we combine this with the dt we choose, so the dt was 0.2, then we get a fifth of that, so it would be 12 time units. So for instance, if you choose a unit system with seconds, that would be seconds, 12 seconds of correlation with the reference solution. There's of course a lot of room for improvement, as mentioned earlier already with the mean in RMSE, but I think that's still a decent thing, especially if you think about it like that. The network is only trained to do one prediction into the future. So it is never trained explicitly to work on its own out, and still it works. It's very surprising to me, and it works quite decently for a couple of steps. I mean, obviously, of course, if you go back at investigating how these windows looked like, so the difference was not that big. And if you now kind of extrapolate a little bit and see how big will the difference be after 20 steps instead of one step, it will still be not that big. but I think it's still an impressive achievement for this neural network that it is able to do such that. But now I think very interesting is also to see how does a prediction trajectory from the emulator actually looks like. And this is what I think is even more remarkable. So let's do an image of the test prediction. Or maybe let's add some note here regarding the correlation, because I also had that in my script. And there I actually checked the 0.9 threshold. So let's maybe write that down. So let's say after 50 steps, we have this, okay, this is like the 0.9 threshold might be around 50 steps. So let's say after 50 steps, correlation is below 0.9. So we kind of crossed this high correlation threshold, and we can then say hence with dt being 0.2. This means 10 time units of high correlation. Okay, cool. So let's use the test trajectory, and let's just use the 0th trajectory and say plt.imshow on the test prediction, 0th trajectory, all time steps, 0 channel, because we only have one channel anyway, and then colon for the number of degrees of freedom, dot t again, because we want to have the spatio-temporal plot flipped. Then I want to set this dmap again to rdbur, and the vmin to -2 and the vmax to 2. Oh, sorry, that was incorrect. It should not be quotation marks, it should be 2. Here we go. So this is a prediction made from the network. Let's also have the test trajectory next to it. So let's have the test trajectory next to it and see, interesting. What do we see here? So first let's check the following. We saw that correlation is high until 50 time steps. So here's 50 time steps. Let's take a quick look at the reference solution. Okay, well, or maybe I will zoom out a bit for you so that you can easily compare the two. So let's look at some distinct features. So maybe we have this region here in a test trajectory, and we also see it here in the prediction. So we also see this region. Let's maybe look at that feature, which is between 50 and 100 steps. Okay, it's no longer visible. So this has chosen a different path. I mean, this also underlines this chaotic nature of the KS equation, that those deviations can easily occur. What I find interesting is, if I just give you this image or this trajectory, it still looks KS-like, doesn't it? I mean, even if it's no longer correlated with the reference trajectory, it could still be a good emulator, because an emulator might not necessarily just be producing the same thing as the reference. It must be producing something that is helpful and that is something that is comparable. So what we should be actually looking at is if the solution manifold that is produced by the emulator is the same as produced by the simulator. And this one can be done in terms of spectra. So we will now look at temporal averaged quantities and see that the emulator might still be a very good guess. So for this, I want to do a very long prediction, because we saw, well, beyond 50, we are no longer correlated and we lost all correlation after 150. So let's maybe do 500 steps into the future. And let's call this the very long prediction. And again, JAX vmap on rollout on the KS emulator. And now let's do 500 steps, because we're going crazy now. And say include init being true, although I think this does not matter here, and then apply it to trg test, because then with trg test :0, we actually start on a point that is on the solution manifold. But now I want to throw away the first 300 steps and only take the last 200 steps, because we saw that once we do more than 150 steps in the future, we are fully decorrelated. So the correlation is below 0. Or is 0. Very long prediction is very long prediction indexed at all samples, and then from -200 onward to get the last 200 snapshots. Okay, how do we get this set spectra? So this is still running here. So for this, we first need to transform the solution into Fourier space. So we will say very long prediction hat is jnp.fft.rfft applied to very long prediction head. So we are using the, to very long prediction, we're using the RFFT because we have a real valued state. This RFFT by default is also applied on the very last axis, which was the spatial axis, so that we're all good to go. And then in order to get the power spectrum, we will take the absolute squared. So let's say very long prediction head abs squared is jnp.abs on very long prediction head and then squared. Taking a look at that, we see this now has 20, 201, 129. Okay, why does this last axis has changed in dimension? That's because we use the RFFT, and the RFFT throws away or ignores approximately half of the modes because we have a real signal. And now we have to take a mean over the first three axes, because we will mean over both the samples. Well, that kind of makes sense. But now we will also mean over time, because for this power spectrum, we are interested in the temporal average. Because with this chaotic attractor, we are moving on the solution manifold. And of course, if we compare two concrete states with one another, they will of course be different. And this is also what we see in the correlation. But we are interested in the temporal average. So when moving around on the solution manifold, when being around the chaotic attractor, do we behave similarly? And this is what we will get if we also average over time. So let's call this the very long prediction head abs squared mean, long name, and say jnp.mean on the very long prediction and now we will make the mean over the axes 0, 1, and 2 to also get rid of the channel dimension. And then we will plot the spectrum with a semi-log y plot on the very long prediction. You get the point, with the x label now being wave number and the y label now being mean power spectrum. And let's also activate the grid. Okay, here we go. So now what do we see? So we essentially have our approximately 125 wave numbers. That makes sense because we are on a domain on 256 degrees of freedom. So the Nyquist frequency will be around half of that. And then what do we see? So we have a peak in the beginning. So on the low wave numbers, somewhere around 10 to 15, we have the highest energy. So that's the mode which carries the highest energy. And then we have a linear decay. Be careful that we are in a log spectrum. So that's actually exponential. And then at a certain point, let's say around 60, wave number 60, we are leveled off, and then we essentially have almost all wave number constitutes equally. But what does that mean, right? I mean, of course, this is the spectrum of the emulator, but is it any good? And for this, we need to compare it with the spectrum produced by the simulator. Okay, let's do the same thing as we have with the prediction, also with the simulator. So we will produce a very long test trajectory by saying JAX.vmap on rollout of the KS-ETDRK two-stepper on 500 with include init being true, applied to U0 test. Sorry, not to U0 test. That's, of course, it's TRG test on :0, because both need to start at the same initial condition. And then we will also take that and extract the last 200 frames from -200 onward. We will transform it into Fourier space. By the way, a quick remark, we saw that this ran incredibly fast, 0.2 seconds, whereas that one took 30 seconds. Of course, it's on a CPU, so networks are not that fast on CPUs. Probably it will be quicker on a GPU with the convolutional architecture, but still we see the pseudospectral method. It's very hard to beat. So if you make an argument in favor of the emulator in terms of efficiency or how quick it is definitely not its strongest point. Nevertheless, let's transform this trajectory into Fourier space. JNP, FFT, RFFT, very long test trajectory. Let's compute its power spectrum. Very long test trajectory head abs squared is jnp.abs on very long test trajectory head and then square it. And also we take the mean, same structure, with jnp.mean of very long test trajectory apps squared, and then take axes being 0, 1, and 2. And then I will copy down this plot and add the reference to it. So plt.semilog on the very long test trajectory head app squared mean. That should be correct. Let's attach some labels to this. So this one is label prediction and this one is label reference. And then we also need to activate the legend. Okay, here we go. So now we have in orange the reference and in blue the prediction. So now we at least have what we should be getting in the power spectrum. Let me also make that a bit bigger, and then we can also zoom in here. So what do we see? Again, we have the same peak for the prediction and the reference. So that is very nice. So we match that peak and we also match this linear decay, but we have 2 parts or 2 points where we do mismatch. So the first, let's look at that. The reference goes down even further. So it has this linear decay going even further down. So at all the way to 10 to the minus 11 at 100 wave number. And this is something you typically see with these convolutional emulators. It's something that's also called spectral blocking, in that the energy is piling up in high modes. So we have here in higher wave numbers, which are supposedly having lower energy, quite high energy. I mean, it's still only 10 to the minus 2, but if we would continue the integration further, one would observe that this energy would pile up and at some point lead to instability. So this is something that is interesting to see. And the other part, which is probably even more worrying, is that the prediction does not have zero mean. So the zero mode is associated with the mean energy, and for the orange curve it goes down to 10 to the minus 9, so in single precision floating point that is approximately 0. However, for the blue one it is not the case. So the blue one actually has quite a lot of mean energy. It is beyond 10 to the 3, and it's almost as high as this second peak here. My interpretation for why the prediction has such a high mean value is because we have biases. So these biases are the additional vectors you add after the convolution, and turning them off might help in not learning this mean energy, but my experience also is that if you turn off the biases, the learning will become harder. So it turns out you need more data or all kinds of other modifications to make the learning work. So it's kind of a compromise. And I mean, ultimately we're looking for emulators, right? So we're not looking for something that is physically fully correct, that is usable. And in that sense, we found something that is actually quite well working. Looking at it qualitatively, we see it is producing something which mimics the KS trajectory. Unfortunately, here it is not necessarily more efficient because we have such a fast reference over. But I think this is a bit skewed because you cannot use pseudospectral methods for any problem in practice, and they turn out to be one of the most efficient methods we have available. So for other problems like other boundary conditions or unstructured grids, one might even see that it is actually beneficial to use emulators. But of course, this is a topic for another video. This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also, a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There is more content on neural emulation, neural operators, AutoDiff, on also writing these pseudospectral solvers. If you're interested in that, then please stick around. You will now find similar videos, and I hope to see you in one of the next videos.